Следующий докладчик Ваня Danyliuk. Он за него очень интересная тема.
А можешь мне включиться? Так, это... У меня доклад будет на английском. Кто-нибудь есть, кто не понимает английский вообще?
Конечно, есть, просто они боятся.
Okay, perfect. I was given a talk last year here in Kyiv Meetups, and I'm actually trying to switch Kyiv Meetups, Ukrainian Meetups, to English, because in any country you go, even countries that historically hate English language, like France, for example, they're doing meetups, all technical meetups in English language, and because right. Yeah, even in, for example, I live in Barcelona, and we're running Golang Barcelona meetups, and Spanish people, they really hate English. Like typical Spanish developer speak very bad English, Spanglish they call it. But anyway, they still try to do all the talks in English, because honestly, given the technical talks and not in English languages have little sense. You can't you can't even post it on YouTube, because you basically limit yourself only with Russian speaking community. So again, I know that's hard to start, but we should, because because like tomorrow you will be hired into the international company, and you will relocate, and they don't care why your level of English is bad. You will have to argue with people, you will have to defend your arguments, you will have to read the technical documentation and communicate with other people. They just don't care that Soviet style schools not good enough. So please come to our meetups, and meetups actually is one of the best ways to practice public speaking skills. We're better than Toastmasters actually, because it's not that level. It's not a conference. You can fail. It's okay. And for example, we have. I remember there was a talk by Alexander Valyalkin, which is really high level. This is the level of talks that you should go to the conferences, GopherCon, .go, whatever. But it should be in English. So please practice. Так, я до нього звертаюсь. Okay, so my talk today, I usually try to make talks that are useful for everyone, something that you can, learn here and take home and apply immediately. But today is not one of those talks. It's a different kind of talk when I'm just going to share the side project I've been working a couple of weeks, and something that I'm really passionate about. So maybe it will be useful, maybe not. I will have some small demo. So the title is the Go as an agent-based model simulation tool. First of all, what is agent-based simulation? It's called ABM. It's a technique in science. It's a technique to explore complex phenomena by modeling simple behavior of simple agents, and then run simulation many times, usually thousands or millions times, and observe complex behavior that emerge from these simple rules. This is opposite to the equation-based modeling, where you have equations. Like think about, for example, solar system model. You can calculate the equations for each orbits, and then just run this, visualize, or calculate, or predict the coordinates of the planets or asteroids. It kind of works, but it doesn't give you the real picture, because you can't predict everything. It will work only as good as your equations are. Agent-based modeling, on the other side, allows you to observe something that we don't know yet. And it's heavily used, I skipped the slide. It's heavily used in economics, in social sciences, especially in urban planning, for example, simulating the escape in emergency situations in large facilities like airports. Sorry. Thanks. Right. So some usually models Models are something that model something from the real world, from the nature, like a flock of birds or school of fish or human crowds or players on the market, on financial market, pretty much anything. One of the examples actually of this equation modeling versus agent-based modeling is famous Lotka-Volterra equations. They describe the changes the dynamics of population in a closed system between prey and predators, like rabbits and foxes, for example. Foxes eat rabbits, and rabbits replicate as much as possible, and they all depend, both of those species, they depend on the food in this closed system. So it turns out that there is a very clear oscillation pattern, and if you run these equations, you will get the same number. But also, if you describe the simple model of this behavior, like eating. If you don't eat enough food, you die. If you age, you die, etc., etc. It gives you the result. So this is a classical example of how agent-based model simulation can be verified by equations or vice versa. The brief history is you probably have seen these terms. So cellular automata was the first precursor to the agent-based simulation. It was coined by John von Neumann and Stanislav Ulam in 1940s, but it was mostly theoretical work. There were no computers at the time like we know them today, right? And until 1970s, there were no advancement in this until John Conway created Game of Life, which is this one. You probably all know this game. This is the simple rules. Each cell can be in two states, alive or dead, and if there is less than 2 neighbors or alive neighbors or more than 3, the cell dies, like if underpopulation or overpopulation. And the dead cell, the white cell, it becomes alive if it has exactly 3 neighbors, like born a new baby. And so simply following those rules, you can observe very complicated patterns. This is, for example, this called glider. This is some static figures. There is a whole corpus of literature exploring the Game of Life. And then in 1980 there was a seminal paper, actually not a paper, it was a contest. The Robert Axelrod created distributed contest to run the Prisoner's Dilemma game. He asked to send him solutions, like strategies. How would you behave in a prisoner's dilemma? This is the game theory classical dilemma. And then he ran this experiment many times and observed how the simulation shows which strategies are better. And then only in 90s and 2000s and years 2000s became proliferation of agent-based modeling software, because computer became more available, they become more powerful, and this is probably the most important limitation of the agent-based computing is that it needs huge CPU power to run. So some examples. Game of Life. This is a crowd simulation. On the right, this is a video from the real Tokyo intersection, and to the left, this is the agent-based modeling simulation. The algorithm here is actually tries to minimize the energy needed to spend by human to overcome the obstacle. So they use some empirical data from the biomechanics, and they ran this simulation and observed this incredible similarity with the real world. And it's actually very useful, for example, to design architecture of the large facilities. So the color here represents how much time needed to escape from the area in case of emergency, like fire or whatever. What's next? All over the world, it's used to plan the roads and intersections and to plan city traffic. I don't know why it's not used in Kyiv. Yeah, there are actually many more appliances, especially epidemic simulation. Pretty much every epidemic starts by simulating how fast it will spread, etc., etc. And I was interested in this because, I don't know, I kind of interested in biology, in economy, and many areas, and I want to be able to simulate this. And it turns out that ABM software that's available in the market is hard to use, complex, ugly, slow, and it's usually Java. It's related, yeah. No, I mean, I'm not mocking Java. Java is awesome in some areas, but not on a desktop. For example, this is what I will show you a couple of most famous tools. The Mason NetLogo, which is probably most known tool for agent-based simulation. As you can see, it provides a lot of triggers, sliders, and sort of grid to simulate, to run simulation. This is Gamma, and by the way, this is prey-predator simulations. This is Gamma. I use this tool until after next update of Java, I couldn't install it. Like install it for over a year. No, really, I tried to reinstall everything. I spent a few days, and I just could not. And most advanced program is the AnyLogic. It's a proprietary software. It's not free, and I think most of the real cool scientific simulation are using this AnyLogic. So and Repast. I haven't tried it. So what's the problem, essentially, with the ABM software? First of all, you need the new programming language to model this, to describe these models. And actually, most of the models are pretty simple. It's not like, you write in the Linux kernel. You just need to describe simple relationship and simple actions, and usually involve some mathematics and some probabilistic counting. So all of those tools, they invent own languages, and this increases the entry barrier by a lot. I don't know how most of the people but I hate to learn the new language because most of languages suck. So the second problem is the UI and interface. It's really hard to make the good interface that will fit all the purposes, especially all the simulations. And simulation could be really different. So they all try to make one universal UI that works for all, and it doesn't work. Doesn't work well for all. Performance scalability. Here's the problem. The latest advancement in the ABM modeling, they use GPU. It's really hard to do. It takes a team of the researchers, and they spend months or two moving the simulation code into the GPU in the GL shaders language. It works only for this use case. So I mean, this is really hard to do. And it's hard to compete with GPU. No matter what you do on the CPU, it will be much slower. And you can extend it to the distributed technologies. You can run on multiple nodes, but again, your software should allow you to do this, and many of those programs do not. So you have bottleneck in performance, and installation issues that I mentioned earlier. Right. Good luck trying to play with even simple model on your weekend. And then I thought, what exactly ABM software does? First of all, you program the model in high-level simple language. Click simple language. I've heard this somewhere. Run many models concurrently. Yeah, that might be rings any bell. Compute interactions, world state, apply algorithms. This is something we do in program languages anyway, right? And present results via some UI. That may be worth exploring, but yeah, sounds like a plan. And I started a side project. It's still in a closed private repository. It's not open sourced yet. So I started to build these components of the ABM software. It's in very, very early stage, but this is how it works. So first of all, you need to write the engine that will will be the core of the program that will connect all other parts and run the simulations. Then you need to write a part that describes the model and allows you to run the model, right? Then you need to implement different worlds. I will talk about the worlds in a moment, because agent may be or maybe not live in some world. It may be not necessarily. I will show you examples. And of course, you need UI, any sort of UI. And those things interconnecting, and this is basically what ABM software is doing. So speaking about the engine, I started implementing it as a simple Golang library. So what I want from engine from the very start is ability to add the agent. Agent is a model, and run the simulation. That's it for now. Yeah, and start the simulation. And actually running the simulation is as simple. Again, we need to run it concurrently, right? And we have this baked into the language. So we don't need to invent any new tools. We just run everything in every agent in own Go routine, and we just wait till the next tick. Here is a point that we have the notion of the time in the world, so we need to synchronize the state of the world between all agents. That's what world tick is doing. The report function I will tell you later, but this is essentially the core of the simulation engine. It probably could be optimized for many edge cases, but in general, this is it. What is an agent? Agent is an interface. Any type that implement run function is an agent. The framework, the library I'm writing, will provide some example agent, but everyone can write their own and simply plug into the framework. So that easy. For example, let's describe very, very simple model of the human that can age and die at some age. So it's just a structure that has this property of age, and usually people use alive, the field alive, to describe if person is alive. But in Go we should make zero values useful, so that bool will be automatically false, so that would be the better choice. Yeah, and then we just define the function run and a couple of actions. One action here is action die, right? So on each simulation run, on each generation, we will increase the age, and we check if we reached the death age, we die. That's simple, yeah. And usually, yeah, and so the language doesn't limit you. This is the powerful thing, because when I was using the gamma simulations, I really had to spend a lot of time reading the documentation for this language and trying to make sense why did they do this exactly this way. It's illogical, and yeah, it takes a lot of time. And in Go, you can do anything that language doesn't restrict you much. And usually, yeah, also for many simulations, you will use random generations with different probabilities observed in the world, like Poisson distributions or chi-square. And there are a lot of libraries that already have this out of the box, and especially I could recommend the GoNum package. It's sort of NumPy for Python. This is GoNum. It's for Go. Next, the world. What is world? With world is a little bit trickier, because world can be spatial. It could have the real locations like x, y, z coordinates. It could be two-dimensional, one-dimensional, three-dimensional. But it could be also non-spatial, like space of beliefs, when you calculate how close beliefs of one social group, for example, closer to another. You can have this XOR distance concept in the peer-to-peer network, and also you can have the graphs and geography data. So I don't really know how to generalize this into interface. The only thing currently that world interface does is it can tick. So one tick is like switch to the next generation. Yeah, and UI. UI again could be very, very different. It could be console, terminal output. It could be native desktop. And by the way, speaking about Gopher.js, I will show a little bit of XShiny. And web-based, of course, WebGL. I should have mentioned Gopher.js, but I haven't tried myself. But it's, yeah, I definitely should try. And here's the point. Different simulations need different UIs. Some simulations don't need UI at all. Maybe you already know what you want to look at, so you just need the output to the console. But again, when you run in the Java desktop application, you have no choice. You have this grid, and you can't get rid of it. So this approach with the Go tool, Go library, gives you much more flexibility. You can choose different UIs at the same time. You can create your own UI. Again, this is just the interface. It can stop and should loop. It's like event loop, like run event loop. And I also define a couple of interface which I definitely will extend. For example, charts. If your UI implementation implements this interface, yeah, it has the method addChart, then it will automatically add you some chart to your UI, just as that. So from the user perspective, you don't even know how this is implemented. You don't care about layout. This is all should be handled in the UI library. And the same with the grid. So the grid and 3D grid is most common UIs used in the ABM software, so I thought it would be wise to implement them as a special interface. So the user code essentially can look like this. Yeah. Oh, right. So we create in the new engine. We create in the new world for the engine. We add in one agent. Just for now, and then comes the notion of the report function. The thing is, UI doesn't know what you're interested in. So your model, your agent can be very vastly different from what UI even care about. So this is responsibility of the user code to count. I don't know, count histograms, count agents, do some analysis of the current state of the world, and report it to the UI. So this approach that I chose, I'm allowing to run the report function that will be fired every time the generation ran all the agents. And this report goes straight to the UI, which already knows what to do. So demo time. I will show you 3 simple examples. For example, let's start with a very simple example of aging. I will copy paste. Come on. So let's go through this code. Creating the new. Do you see code well? Yes. Okay. So we creating the new engine. We start 100 humans, and human. I can show you the library what human does. Human have. Age, it has state alive or death. It has the child age when to create a new child, and the death age calculated with some probabilities. Yeah, I mean, this is pretty random numbers, like a 25 plus minus. How many children? 1.5 children in average, and death age is around 80 years. Right, so we limit iterations to 200. I mean, by default it's 1000, but let's choose any. Then channel that will count alives, how many humans alive in the current step. And so what we're doing, we count in all the agents and return this is the function, just the closure that returns if human is alive. And also interesting thing, I don't care about concurrency safety, like concurrent safe code here, because human, at least in this case, human. So they run the generation, simulator run all humans, and then wait. So they don't run concurrently all the time on the same code. I mean, the same agent doesn't run concurrently many times. Yeah, and then we just report the number of alive people. We run start simulation in a Go routine, and then fire up the new UI and add chart. So let's check if it compiles. It compiles. Go run. Yeah, like this. So it's a very, very simple terminal-based interface. And you already see that it shows some dynamics, which is like not obvious, right? But we can do.
Increasing the number of simulations.
Sorry?
Increasing the count of simulations in order to see how this graph will.
Yeah, the point is this is very simple terminal graph. I can't scroll it. I mean, I can write it, but it's not ready yet. So I can only see the first 300 or 400. So I can show you another, what we can do. For example, let's calculate how many newborns, for example, at this time. So I create a new channel, newborn channel. Make channel, oops. And doing pretty much the same, another counter. Newborns, and the rule for condition will be if age is less than 5. Maybe it's not the exact definition of newborn, but okay. Yeah. Newborns channel. Okay, and then what we do is just add another chart. Newborns.
We are writing.
Sorry?
We have a typo. Newborns, we should write into channel.
You should put.
We are currently
right.
writing the same variable.
Right. Right. Yeah, I see.
And why is the number of people is float, not the?
It's because, yeah, good question. It's because the chart by default takes floats, and I mean it's super easy to convert ins from float, right? Then vice versa, but I mean. The thing is, I don't know the whole space of possible use cases, so I'm currently just trying to create different models and then see what I need to extend, which types. I mean, I still use for example, for the grid, I will show you later. For the grid passing to the UI, I use the interface and empty interface because really there is no way to predict what will be in this communication layer between the grid, between the world and the UI. Maybe when I will see all the options I want to support, I will be able to generalize it and create some good type for it. Let's see. So yeah, newborns. What? Okay, it compiles. So now I should have two charts. Again, UI part takes care about all the layout thing and everything. Yeah, like this. And yeah, so you got the idea. We can do pretty complex thing here. Well, this model is simple. But it just showed the basic concept. Next. Next example, oh yeah, this is the game of life. This is the game of life. The model for the game of life is already in the package. Okay. So what's happening here? I have a model Convey Life. I'm creating the new engine, creating the new grid. Grid is a special world. It's already implemented in library. It's a 2D grid, size set to the terminal size. And then I populate each cell of the grid with random value of either alive or dead. This code probably could be much simpler, but anyway, for now it's 3 lines. I'm creating the new cell, adding agent to the simulation, and I set the cell in the grid. And and this is what I was talking about. Into the channel, I pass the whole content of the grid, and to define which part of the grid will be enabled or disabled, I use the function which is alive. And here's the model. And here's the model of model of the game life. We count neighbors. This is the code. This is the code from the grid package. And if cell is alive and neighbors less than 2 or more than 3, we die. Or if it's not alive and neighbors exactly 3, we reborn, right? So we run live go. This one. I just switched to another UI, and all the rest is just, you know, they satisfy the same interface. So let's run it. Yeah.
Can you control the speed of simulation?
I can slow down it. Yeah, I can slow down, and yeah, this is, you know, you can do anything. You can wait for the user to press enter. You can add some widgets to, you know, to move forward and back. Oh, actually, this is slowed down. This is 10 milliseconds between each iteration. A bit faster, yeah. But currently, I'm not trying to optimize the performance. Currently, it's really slow compared. Actually, here's the thing: if you want to write, for example, Game of Life, just Game of Life, there are much better, much faster approaches. You can optimize it to the crazy speeds, and, you know, write some decipherable code that I actually wanted to put the example I found on the GitHub onto the slides, but I forgot. The code that run the simulation in Go, but you can't figure out the behavior of the single agent. They codify these rules, they applied some crazy optimizations to run it as fast as possible, but you're losing the expressivity of the agent simulation. So maybe the Conway game is not the best example, but for more complex simulations, you will not be able to use those optimizations. So, for example, one of the approaches actually of using simulation in the native in the programming language like Go is that you can run real code that already is written in Go. For example, I will show you a slide here. This is something I work on my daily job. This is simulation of the peer-to-peer network, Ethereum network, and a propagation. So in Ethereum, there is a protocol called Whisper that essentially a peer-to-peer messaging protocol. And here's the simulation that I run to visualize the propagation of the message through the network. I don't know if you see this in the red color. And so what happening here is I'm actually running for all these octahedrons. I'm running the actual code of the get of the Go Ethereum, official Ethereum Go implementation. And I'm running the simulation, and I'm then just collecting the data from the channel and visualize it. It's pretty much the same approach. And good luck implementing Go Ethereum peer-to-peer stack in Gamma or in NetLogo or in whatever. It's just close to impossible. So yeah. All right. So the next example I want to show is the random walk. Random walk is a concept when you just put the point into the space and you allow it to walk randomly in any direction at any point at each tick of time. And it turns out that behavior of this very simple model describes many processes in the world, like Brownian, I think, Brownovskое движение, Brownian movement. Sorry?
Bitcoin prices.
Actually, you're not too far from truth, because there are models based on the random walk that predict stock prices and for the cryptocurrency as well. Well, this is very at the field of research, but I don't think I'm aware of all implications. But this is like really important concept in stochastic simulations. So this is how it looks like. You just allow things to run. They calculate then average distance the point goes, etc., etc. So let us implement this in Go as well. Random walk. Yeah, here what I'm doing here again. This is 2D grid. I'm using the already written model Walker. I can show you the model. Yeah, this is the agent code. I randomly generate the number and just move the cell in any of direction on X and Y axis. And the trail is just a flag that tells whether you should preserve the previous position in the grid or not. Yeah, and basically that's it. That's the whole model. Set cell. Report function, the same as in the previous example with the Conway game of life. Start simulation and term grid, this super simple UI. You run and walk. Okay. Now let's change it a little bit. Sorry. Again, let's use Shiny. Okay, Shiny. That would be, let's say, 300 at 200. Kemas term grid I don't need. Okay. Oh, it's too short. Set limit iterations. And I can run many agents actually. I can run, let's say 5.
Color.
Yeah, this is something I haven't finished. Yeah, I was working on it like 2 weeks, but that's the next step.
Okay.
Yeah, without colors is harder. But let's try this in 3 dimensions. Yeah, I will show you already made a pre-made example. So in 3 dimensions, essentially the code is essentially the same, but we just add the z axis, third axis, right? We define the number of cells, 10,000 simulations. Yes, and for the UI, the same way UI is just plugged in, it's just interface. And for the UI, I'm using the library that starts the WebSocket server, then starts the HTTP server, launches the browser, and so the JavaScript code. I actually, yeah, answering your question, what's the problem with frontend? I had to write frontend for this, and I hate it. I just cry every time I need to write JavaScript. I cry with blood in my eyes. This is terrible. No, I mean, I'm not disrespecting JavaScript. I think people do an amazing thing in JavaScript, but they're doing it not because of the language, but in spite of it. Yeah, and so that's how this UI works. It launches the JavaScript code, which talks via WebSocket to the backend, and backend launches the simulations, and via the channels send the values to them. So this is how it works. It's not super cool. It's actually very two-dimensional sprite, simply for the performance optimization, because it's much faster to draw the sprite than like real 3D object. If you want to run, thousands of objects. So this is the 3D grid. This cube represents the world, and this is the random walk in 3D. But we can do even cooler. We can do. So I think I have this in this code. We can run, for example, 10 cells. Yeah, so that's probably not very interesting for us, but this shows the potential of this approach to the agent-based modeling. Yeah. Okay. So let's back to the slides. Conclusions. First of all, Go is a model language. I think it's a really good fit because those simulations are usually written by scientists. And I don't know if you have exposure to the scientific community, but they hate all the modern practices. They don't read books on how to use, this feature of the language or different feature. They just want to get the job done as fast as possible. So the simpler the language is for them, the better. Again, the example that I showed you with the peer-to-peer simulation, this approach allows to reuse existing software. And what is more important for me, it's testable. You can write model code and run simulation and just have very tiny error and just get wrong results. With Go, you can test it very well and be sure that you get the results you really want. Performance. So as I said, nothing can beat GPU. So I personally see this as a tool for preliminary exploring of the model. So I run it on small scales. I verify the idea. I play with different parameters, and only then, when I want to run the real simulation, because real simulations usually needs billions of iterations. They need millions of agents, and they usually run on the supercomputers or on GPU. So this is not will never match the performance of the GPU, and none of the languages will. But in current state, there is a huge space for further optimizations. For example, in the grid code, the code currently how I calculate the numbers or distances, it's very, very straightforward, and you can rewrite it in assembly if there is need to. And there is good flexibility because you kind of offload a lot of things to the user code. So user also have a huge space to optimize. In those existing Java tools, you're just limited with what your software does and gives you. You can't optimize it further. And speaking about UI, this is the line that literally repeats what Alexei said, that we don't have out-of-the-box high-level UI solution. And I think there are valid reasons for that, right? We don't write desktop software anymore. We all use the web software. But I think with advancement of WebGS, there will be a new era of the good UI frameworks. And but at the same time, we have more options than in traditional IBM software because we're not limited with what software gives us. We can implement everything we want. And what is important that every developer, every researcher that use this framework can implement. Technically, it can. Probably they will not, but they can implement their own UI. Maybe they need just to pass the data into existing program. Maybe, I don't know. I can't predict everything, right? Awesome flexibility, switch between console to WebGL. Yeah, that's it. Thank you. If you have any questions, I will be available. Yeah.
Maybe about running computation on GPU. What are you using, or what you plan to use?
I don't plan to use.
No.
This is crazy.
Is there any bindings in the code?
No, this is crazy. It's not about bindings. You need to convert your model into the GPU into the GL shader language, and it's not like straightforward translation.
I actually heard and find some libraries. I don't really remember on which language. I guess on Java that they provide such like reach, so you can write.
Oh, really? That would be awesome. Actually,
I
cool.
actually can find it.
Okay.
Sure.
Yeah. Cool. Thanks. I will be interested to explore it. Yeah.
Why didn't you pass the world to agent, to run function of that agent?
Say again. The world.
I think that it would be better to pass the world.
Agent has an access. Agent has an access to the engine, and via the engine it has an access to the world. So definitely, yes. Agent should have access to the world.
So this in your interfaces.
It's not necessarily a thing. not every agent need the world. For example, this human age example, they don't interact, so they don't need world. They just need to,
Most models actually need.
Yeah. So I think it's models. Let's say random walker. Yeah, here. So at the initialization of the agent, I read the world. If there is no world, I fail, and I take the grid because this agent can live in grid. Yeah, so you have an access.
Have you already implemented some kind of technique to communicate between agents, some kind of like ACL protocol?
Good question. No. I think I will have to do this, and what I'm thinking is to again use what we already have, the channels. So if they have neighbors, they can connect with the channel and then use whatever they want.
Yeah.
Actually, that will be important for mocking the networking layer for the peer-to-peer simulation. That's something I will be adding.
Yeah, in this way you would be able to block the agent while waiting for some specific kind of message.
Yeah.
Yeah, that would
Cool.
be great. Thanks.
Cool. Good question. Yeah.
Yeah, I would just want to ask about, did you find any not UI-based software to, like, I feel that something is living in private closed repository that someone is using in other language. So you actually are comparing like your tool to attempt to optimize it for less programming people.
Okay.
Like NetLogo and such things. Maybe out there's like more software.
In private repositories.
Yeah.
Maybe. I have no access to the private repositories. They private.
And like those languages in those UI programs are supposed to make people define models easier. And if they need to go deeper, they need to learn any language. So you propose to learn Go for great good.
Yeah, right. But Go, Go, if you already have some basic knowledge of any programming language, to learn Go, I don't mean like standard library, but just to get grasp on Go, it takes like a weekend. So I think if we're going to ask people to learn new language, it would be better if it's Go. Yeah.
Can we use your project like a small game engine, for example, for simple multiplayer games online? Because your concepts are the same. The world is like a game world, engine is like layers or walls, and for example, I can use your engine like as I said, simple engine for multiplayer online games.
Yeah, there are actually many common patterns and common things in. But I think at this point that would be vice versa. I will have to learn more from the game developers because they face many of the problems I have, like optimization. For example, if you try to describe the physics with this modeling approach, you will have. I mean, you can define the forces between the objects and calculate like force that every agent attracts or reflects. Okay, we'll find out. But that will be very slow, so you need to use a lot of optimizations. But at some point, maybe yes.
Some simple projects like 2D games where I have layers, guns, and shooting them.
Yeah, you have ability to create your UI.
Я прошу прощения, что вас перебиваю.
Sorry.
Было вообще заявлено 2 доклада, но как это получается на метапах, у нас есть еще один спикер, и он выступит через 10 минут, потому что приехала пицца. И можете продолжить общение